Nitrification is the microbial pathway that is central to wastewater treatment. The 21st century grand challenge of ecosystem protection is closely related to the National Academy of Engineers, or NAE's, grand challenge of managing the nitrogen cycle. Studying nitrifying bacteria and nitrification allows for environmental engineers to design better conditions for nutrient removal. Without it, wastewater effluent will have high concentrations of ammonia. Maintaining the success of nitrification in wastewater treatment is significant in addressing the specific grand challenges of: first being curbing climate change. Algal blooms from excess nutrients release nitrous oxide, which contributes to climate change. Nitrification lessens the nutrients in the effluent released back into the environment. Second being designing a future without pollution or waste, as nitrification reduces ammonia or pollutants from entering the environment. And third being to create efficient, healthy, resilient cities, as creating healthier, cleaner effluent leads to healthier and resilient cities. When wastewater is left untreated by nitrifying bacteria, the nitrogen-rich effluent released to the bodies of water, like rivers and wetlands, can lead to eutrophication. Nitrification in wastewater is essential to reaching the goal of protecting the ecosystem.
To begin with, nitrification is one of the most important steps in the nitrogen cycle, which is the process by which compounds containing nitrogen are converted between each other as they circulate through the ecosystem. However, nitrogen in the form of ammonia and ammonium can be toxic to aquatic life and contribute to eutrophication and an overgrowth of algae, potentially creating dead zones in the receiving waters. Thus, nitrification is important because it is a critical step in removing ammonia during wastewater treatment and protecting receiving waters. To do this, ammonia oxidizing bacteria, or AOB, first carries out the following reaction to convert ammonium in the wastewater effluent to nitrite. This reaction has a Gibbs free energy change of negative 91.55 kilojoules per mole per electron, meaning that it is spontaneous. Then, nitrite oxidizing bacteria, or NOB, converts the nitrite from the AOB reaction into nitrate. This reaction has a Gibbs free energy change of negative 37.07 kilojoules per mole per electron, thus making it spontaneous as well. When both reactions are added together, the spontaneous overall reaction for nitrification is ammonium plus 2 oxygens equals nitrate plus 2 protons plus water. Overall, the electron donors in this reaction are ammonium and nitrite, while the electron acceptor is dissolved oxygen. As a result, nitrification decreases the toxicity of the water and effectively converts the ammonia and ammonium in wastewater to nitrate, thus preventing dead zones from forming in the receiving waters.
Some common characteristics of nitrifying bacteria are that they have a rod-like shape, have flagella to help them move, and require O2 or oxygen. The bacteria typically live in nutrient-rich environments such as lakes, rivers, in a pH of 6 to 8, and in temperatures of 65 to 85 degrees Fahrenheit.
Nitrification is vital in the environment and especially when it is present in water treatment systems. That's why it is an important topic for research within the environmental engineering field to learn more how it works. Nitrification in water and wastewater treatment is important to us because nitrate is the preferred chemical form over ammonia. Analyzing different conditions of nitrification leads us to the best possible way to achieve the highest efficiency of nutrient removal. Based on current research, nitrification is optimal with the following conditions. 1. Detecting certain inhibitors, also known as a substance that slows down or prevents a chemical reaction. Stopping the inhibitor successfully completes nitrification and produces cleaner water. 2. Having thicker biofilm during treatment, also known as a slimy layer of bacteria. This means less nitrification but more nutrients are removed, which is good. 3. If the water is dirtier, nitrification is being performed at a faster rate. That means if we feed the bacteria nutrients during water treatment, they can clean the water faster.
As discussed, it is beneficial to apply nitrification to solve the environmental engineering challenges of reducing climate change and pollution. This is because nitrifying bacteria allows for the removal of ammonia, nitrate, and nitrite from wastewater. As a result, there are less nutrients released into the ecosystem. Some expected outcomes of nitrification is a reduction in environmental hazards. Thus, this tackles the NAE's challenges of curbing climate change, designing a future without pollution or waste, creating healthy, efficient, resilient cities, and the UN sustainability goals of achieving climate action and making sustainable communities.